All right, I think we can get started. My name is Sudarshan. I'm from Qualcomm. I work in the Linux kernel team from the past 8 years. And the topic for my talk is how do we dynamically resize a secondary VM, that is a virtual machine. And this will be mainly a guest-driven approach where we dynamically try to expand or inflate or deflate a secondary VM. So here's a bit of an agenda. I'll talk a bit about myself and the team. And I'll give some context about what is exactly this resizing of secondary VM is and how do we add extra memory from, to the secondary VM. And then I'll explain about the memory detection technique that we have in the Linux kernel. How do we use that feature in the Linux kernel to actually detect memory pressure and memory demand happening in the system. And I'll talk about the VMRD, that's the VM resizing daemon. It's a user space daemon that actually detects memory pressure and then adds and helps to add and remove extra memory in the VM system. So this is something that we wrote from Qualcomm, and we have been working on this in the past 2 to 3 years. So I'll explain a bit more about the VMRD daemon that we have, and then some of the challenges, limitations, and technical details about the whole feature. So about me, I work on the Linux kernel team since 2017. I'm part of the Qualcomm Innovation Center, Inc. My main work has been in the memory management side for the Linux kernel. Ever since I joined Qualcomm, I've been doing other things for the Linux kernel. And I do have interests in, mainly in kernel development and also in system design, firmware, embedded systems, and computer architecture as well. And here's my LinkedIn link as well, and feel free to connect with me. So resizing the secondary VMs. So actually, in the whole discussion, this will be a design where we have a secondary VM that is on the right side, and we also call it as the guest VM, and we have the host VM here, which is called as the primary VM. And then the secondary VM is actually running Linux, so I'll be mainly focusing on Linux. And then we want to expand or inflate the secondary VM with memory. And how do we do that? And that particular memory will be coming from the primary VM. So it's not like the secondary VM, we just like the DIMMs, we add extra memory externally. So this is actually coming from the primary VM itself. So to give a context here, you have this primary VM, you have the secondary VM, and then one of these two will request saying that, hey, the secondary VM needs more memory. And then the primary VM will do some allocation, transfer that memory to the secondary VM, and then secondary VM will attach it to its IPA space, that's the intermediate physical address space. And then secondary VM attach that memory into the system RAM. And that memory is now available for any applications, user space, even kernel as well. Things like malloc and kmalloc. And then once the secondary VM is done with that memory, let's say the use case started, it used this memory, and then the use case end, and then it doesn't need that memory, extra memory anymore. So the secondary VM can decide to give this particular memory back to the primary VM. So there are different ways to do this. So I'll just, for the sake of explanation in generic terms, we have two things, one is the host-driven, and then the second is the guest-driven. So the host-driven is primarily the primary VM or the host will actually determine that, okay, the secondary VM is actually going out of memory or there's more memory demand in the system, in the secondary VM system. And the primary VM is the one that actually initiates the memory transfer. And then once the SVM secondary VM is done using that memory, it will give back to the primary VM. So here, in this case, it's a host-driven, meaning the primary VM will have access to SVM, it'll probe, seeing that, is the secondary VM running out of memory, and then the primary VM will actually initiate the memory transfer. And the second one is the guest-driven, where the primary VM itself will participate in requesting extra memory. So the primary VM, we know that it's running out of memory, and then it'll ask the PVM, the primary VM, that, hey, okay, I need some more memory, can you transfer some memory? So this is mainly a guest-driven approach. So resizing of the VM based on memory demands, meaning we want to actually increase the memory in the secondary VM only when there's memory pressure. so that I can actually boot up the VM with a small memory footprint, sufficient to boot the kernel or boot the Linux and boot to shell. And then if a use case is running in the VM, then I can plug in more memory to the SVM. So this is all done based on memory demands. And then similarly, once the secondary VM is done using that extra memory, and it finds that, okay, we don't need this extra memory anymore, and this extra memory now can be given back to the primary VM. So this is mainly something called as the memory, dynamically resizing the VM based on memory demands. And we'll be talking about the guest-driven approach where the primary VM is the one participating in the, requesting the memory from the primary VM. So there's something called PSI, pressure stall information in Linux kernel. It was originally implemented by Meta, and then today all the kernels, or mainly the scheduler, actually uses the PSI mechanism. And then we use the memory pressure detection using this PSI that we have in the Linux kernel. So PSI basically tracks process stalls. For example, process stalls on resources like I/O, CPU, or memory. In simple terms, let's say you have a process doing malloc of, let's say, 20 megabytes, and then the kernel has to do something to get those 20 megabytes. So the process waits for some time, it goes to sleep. So that process stall, the amount of time the process stalls is captured by PSI. And if it goes above a certain threshold, then it can actually generate an event, an ePOL event. And then it can give to the event to the user space saying that, hey, there's a memory pressure that happened in the system, and then user space can decide to do some actions. So it also gives something called averages. So you have PSI tracking for I/O, CPU, and memory. So it'll be all under proc pressure slash I/O or CPU or the memory. So we'll be focusing on memory because this is memory demand based in resizing of the VM. And we have like 3 averages here, like average 10, 60, and then 300. So this says like the amount of time that process has been stalled in average window of 10 seconds, 60 seconds, and then 300 seconds. And there are 2 terms, sum and full. The sum is, it says that if there's actually at least one process that's stalling for memory, so that will be captured by the sum. And then if there's all the processes in the system are being stalled because of memory, then it'll be captured as full. And this is something more critical where all of the process in the system is stalling for your memory. And PSI has something called as the PSI monitor. This is more of a sampling mechanism where if your process enters into stall state, it'll start sampling every, in a given period of time. And then it activates an event if the process stall is above a particular threshold. And user space can actually listen to this events. It can register this PSI events. It can have its own thresholds. If, for example, let's say 10 milliseconds or 50 milliseconds of process stall. If so, then give me an event. So the user space can actually register to this PSI monitor. So here's a graphical representation. The blue line that you see here, this is the amount of time that the process gets stalled because of a resource, which is memory here. And you see that it is empty here, and then, for example, let's say it does a malloc over here. And then as time, the process stall increases. And then if the stalling happens and if it goes about a certain value, then it triggers the PSI monitor. And then you see all these vertical lines that actually activates, and then it keeps sampling your stall for every 1/10 of this whole window cycle. So this is your whole window where after the end of this window, it will tell how much the amount of time that the process was stalled. And if it's above a certain threshold, for example, this line here, so you see that the process stall is going above this threshold within this window, and if it does, then it will actually give an event to the user space that has registered to this particular threshold here. And here it will calculate the linear stall that happened, and then at the end of the window, it will actually give you an event to the user space saying, this process stalled for X amount of time or X amount of milliseconds. So here's a real world kind of a thing where we are using PSI in our system for Snapdragon. And then if I launch an app, let's say a camera app, and then camera app is a very memory intensive. So you see this black line is actually the total pro stall, and this is all for the memory. And then the other colors are for like, you have compaction, thrashing, and other things. So you see that once I run a use case that is memory intensive, the stall spikes up and then comes down. And then if it goes beyond a particular threshold, let's say 200 milliseconds threshold, it can be considered as, okay, hey, there's a memory intensive task that is running, and the system might need more memory. And I do want to highlight this area where, after some ups and downs here of the stalls, and then once the use case ends, so for example, in this side, the use case ends, I close the camera app, and then there's no more stall happening here. So this over here, it's an idle stall, so this can be considered as an educated guess where, okay, there's no memory-intensive task that's running in the system. And it can be considered that, okay, memory that was added previously to accommodate this whole memory demand, and now it's no longer needed here, and that can be given back to the primary VM. So this is a nice real-world representation that happens where your process stall keeps going up and down. I mean, once you run a use case, your stall goes up. That we can monitor it, and then the event can be generated, it can be given to the user space, and the user space can decide what to do with this. So here, one example is in Android, the LMKD, or it's called as the low memory killer, daemon, LMKD, that actually uses the PSI to track what's the process stall happening due to memory, and if it's more than a critical value, then it decides to kill some apps to free up some memory. Just like the scheduler that we use today in the kernel that uses PSI, the LMKD as well in the Android uses the PSI for monitoring and detecting memory pressures. So VMRD, this is the daemon that we wrote. It's purely native. It's running in C++. It's running on the user space of the VM. It registers to your PSI events over here. And then, as in when you get an event from the PSI mechanism, it'll know that it has the pressure has gone above a particular threshold. Then it knows that, okay, there's a memory-intensive task that's running. And then it can decide, okay, hey, maybe the system now needs more memory. So the VMRD now is running in user space, and it communicates with a kernel driver within the secondary VM itself. And this kernel driver can now do the whole remote allocation where it talks to the primary VM via the hypervisor, and it can ask, the primary VM can ask for the secondary VM can ask from the primary VM that, hey, there's a memory-intensive task that's running, and then we need more memory. So this whole thing, in the kernel driver, we actually use something called the memory hot plug to add extra memory and then also try to remove those extra memory. I will tell more in details about the technical aspects of it in the later slides. And then using memory hot plug in ARM64 targets, we have memory blocks of 128 MB. But there's also some changes that we did where you can actually add smaller chunks as well, such as 4 MB. So yeah, this is a user space daemon, which is open source, purely written in ADC++, and it's running on the secondary VM, and it is CPU agnostic. It can run on any Linux that has config PSI that's enabled, and it can do all this memory pressure detection and things like that. So here's one simple illustration where this whole window can be tuned or fine-tuned based on how it needs. So it can say that if it sets the window as 50 milliseconds, then your PSI monitoring, which is 1/10 of it, the whole sampling is 1/10 of the window, which is 5 milliseconds. And the reason we did that is we want to track even the smallest increase in the pressure. Like even if there's a small process doing malloc and the stall is more than, it's very, very, very small, even 5 milliseconds we want to track, and the VMRD should be able to do decisions based on that pressure. So we want to make sure we track the smallest memory pressure as possible, and then we detect the memory-intensive task as soon as possible, and then we try to add the blocks as much as possible. So here's one simple example where you have your secondary VM here, and then you have a use case that runs malloc, and then due to the malloc, the kernel tries to free up some memory, and then because of that, it puts the process into stall, and then the process gets stalled more than 5 milliseconds, and then the PSI mechanism in the kernel generates an event, and then that event is being given to the VMRD user space, and then the VMRD also checks, system stats. It checks that is there enough free memory, or if not, let me communicate with the primary VM and then ask for extra memory. And then the primary VM now allocates this chunk of memory and then adds it to the secondary VM. So I talked about how do we detect pressure and then add extra memory when the pressure is there, right? So how do we now detect pressure going down, or how do we detect that, that process that was there, that done malloc, and then that process exited? And then how do we know that the process exited and then now there's enough free memory in the system and I want to give it back to the primary VM? So there's no PSI kind of a mechanism that actually detects pressure going down, but we can use all these averages that I mentioned, where if you remember in the previous graph, this side. So we can see that we can wait until there's no pressure at all, and then we wait for some time, let's say 10 seconds, and then we wait for the pressure to decay exponentially down, and then we check the memory stats, and then if the memory stat says, for example, free memory is 20 megabytes, and that 20 megabytes now can be given back to the primary VM. So basically, there's idle pressure, there's no PSI event, you wait for a certain amount of time, for example, let's say 20 seconds, and then you actually wait for this whole averages to kind of decay down. So this is again an extra layer saying that the pressure decay is actually going down, and it's going in a downward trajectory, meaning there's no memory-intensive tasks running. And we have a check that says, is the averages below a certain threshold that we want? For example, these values. And then we say that, okay, if the pressure has come down and decayed until this value, and there's no new pressure until this time, then we can take an educated guess that there's no memory-intensive task that's running. So now maybe let's see how much is the free memory, what's the memory stat in the system, what's the free memory. And if there's enough free memory in the system, for example, let's say there's 20 megabytes, then we know that the secondary VM doesn't need this 20 megabytes because there's no use case that's running that's using up this 20 megabytes free memory. So now the secondary VM can now decide to give that 20 megabytes back to the primary VM. So we use this wait for idle and then pressure decay mechanism to kind of take an educated guess that the whole memory-intensive task that was running previously, that allocated memory, and then we installed some more memory in the SVM. It's no longer needed, and then that memory that we added before now can be given back to the secondary VM, to the primary VM. So this is this 120 megabytes. It's from the memory hot plug. So Linux has something called memory hot plug, where it's just like DIMMs. For example, you have your laptop, and then you want to expand your RAM. So what do? You just get the extra RAM, and then you just plug it in. And if you're having a Linux system, the memory hot plug is what it's getting run, where it can add this amount of memory to the system using memory hot plug. And that particular memory is now available to the whole system as system RAM. So we use this memory hot plug for plugging in and removing this extra memory in the secondary VM that we got from the primary VM. And for ARM64 targets with 4 kilobyte page size granularity, the block size is 128 megabytes. So now this is the minimum that the memory hot plug supports. So if I have a malloc, let's say, of 20 megabytes, I don't want to add this whole 128 megabytes. Maybe I might add, let's say, 24 megabytes, or even smaller than that. If I have a malloc of 1 MB, I don't want to add this entire 128 megabytes, because this 120 megabytes is the minimum that Linux supports with memory hot plug. So what we do is we do something called as the fake add, where we add this 128 megabytes and then make it inactive, meaning that the pages inside that, the flags of the pages we set as offline and then dirty, meaning that these pages, for example, this gray area here, those pages are installed in the IPA space, but they are not yet available to the system, meaning the pages are all inactive and they are offline and they are not available to the system yet. And then when I get a pressure, I can add the smaller blocks, let's say 4 megabytes, which is the smallest resolution that we can add, and I can add this 4 megabytes one by one. So once I add this 4 megabytes, what I do is, in all of the 4K pages inside this 4 megabytes, I remove those flags that were set as dirty and then offline, and I call something called alloc contiguous range in Linux that adds all this 4 megabytes into the system RAM, into the buddy allocator in the Linux. And now this whole memory is now available to the system RAM, and any process or even the kernel can use this memory. So we can split this whole 128 megabytes into smaller chunks so that we have a very smaller resolution right now where we add like 4 megabytes one by one. And we also use something called as the memory on mem map, which I'll explain in the next slide. So the memory hotplug supports something called memory on mem map, where for this 128 megabytes, the Linux also, for its metadata, it stores the struct page array for this whole 128 megabytes, which is called as a mem map in Linux. So memory hotplug allows you to install that mem map data within this 128 megabytes itself. And the reason why this is important is I can literally go from 0 till expand to how much I want, because entire memory that even to kind of manage and do bookkeeping for this 128 megabytes can also come from this within this whole extra newly added block that we did. So basically I can go from 0, and then the kernel doesn't need any extra kernel memory to do all this hotplug stuff. So here's one simple sequence where I add this 128 mega memory block, fake added, meaning virtually added, and then make all the pages set as dirty and then offline. And then once I get a pressure, once the secondary VM decides to add more memory, what we do is we allocate in terms of 4 MB chunks from the primary VM, and this allocated memory is now given by primary VM, and then the hypervisor installs it into the IPA space of the secondary VM. And now to make sure that this memory is now available to the system, what I do is I just install them in this virtual 128 MB block, and then all of the pages within this block, I clear this flag which I said before, the page offline and then page dirty. And then I call something called as the alloc contiguous range, where from this start to this end, to make sure that this particular memory is now available to the system RAM. So some of the challenges and maybe the limitations as well. There is a bit of a time that you need the process to stall to let us know that there is some bit of a memory pressure happening in the system, and there is some memory, there's some process that's actually doing some memory allocation. And we need to stall for at least 5 milliseconds so that a PSI event has been generated and then it's given to the user space, and then the user space can do its action. So you need to wait for at least a minimum of 5 milliseconds delay for the whole process to stall. So there's a bit of a latency over there. And of course, since we are in the virtualization area, there will always be some latency incurred between communication round trips between the primary VM and the secondary VM. For example, the secondary VM has to communicate with the primary VM saying, hey, it needs more memory. And then the primary VM now allocates memory and gives it back to the secondary VM. So that whole round trip, it incurs delay because they're all going via hypervisor, and the hypervisor has to do some work. The primary VM also has to do some work, and the secondary VM also has to do some work. So there's a bit of a latency that's incurred. So while we want to remove the memory when it's no longer needed, we use, again, a memory hotplug to offline or unplug that memory. And while we do that, it's possible that there's something called page pinning, where there's a particular process in the user space or in the kernel that can actually pin a particular process. So pinning of that page now hinders it from getting isolated and then migrated out. So there are chances that a particular page can be pinned and it cannot be offline. And the whole relinquishing where the opposite side where we detect the pressure going down and then we see that there's extra memory in the system and we want to give it back to the primary VM, it's all based on estimation. Whereas in the opposite side where the detection is much more robust because of the PSI events, but the opposite side where we want to detect the memory the pressure going down, that's all based on estimation, using the averages and exponential decay and everything. So in terms of the implementation, the ones that I mentioned in this side, so this is all supported in a particular driver today, and it's all done in the virtio-mem driver, if you guys are familiar in the Linux area. So virtio-mem driver supports this whole concept called sub-blocks and then the main blocks, where it splits the whole 128 megabyte memory block into smaller chunks called virtio blocks. And it does the whole thing of offlining and onlining and making sure the pages are offline. And then when the memory is added to the system, it does the onlining and everything. And we use the memory, the virtio-mem driver to do most of the memory hotplug stuff. And it leverages the memory hotplug feature that we have in the Linux. And what we have done is to fit our need where the user space can communicate with the virtio-mem driver and the kernel. We have done some modifications to the virtio-mem driver where it allows the user space to also communicate using ioctls to the driver in the kernel, saying that the user space can now request the kernel to add more memory, and then the SVM can do its action to talk to the primary VM to add some more memory. And the virtio-mem driver in upstream doesn't have the memory on hotplug feature, so we added that support to the virtio-mem driver. And another important thing is, if some of you guys are aware in the memory management side of Linux, we have something called the movable zone. All of this adding and removing of the memory in the secondary VM, it happens in something called the movable zone. And we use movable zone because it guarantees that the pages can be actually offline and then isolated and then migrated out. So this is very important for offlining those 4 MB chunks and giving it back to the primary VM. So we use movable zone for that, and then 90% of the time it guarantees that the pages can be offline. So this whole idea of dynamically resizing the guest VMs or the secondary VMs, we had communicated with upstream as an RFC. There's a whole lot of discussion over there. And we did get some ideas and optimizations from the upstream community. So I've put the link for that discussion over there. And we have also shared the open source code, the native daemon, the VMRD daemon that we wrote to the upstream community maybe 2 years back. You can find that code in this link. And some of the modifications that we do, that we did to the virtio-mem, to the upstream virtio-mem driver, we have our own Q2I virtio-mem driver that actually talks to the original virtio-mem driver. And the support for memory and mem map and everything, you can find it in this link. So the advantage of all dynamically way of doing is there's no admin intervention over here. Meaning the SVM can itself add the memory naturally if there is memory pressure. And as I said in the beginning, the VM can boot up with a very small footprint, and then it can expand its memory when there's pressure or when there's use case running, and then it can deflate its memory when there's no use case running. So this helps you to keep the idle memory footprint of your VM very, very low, and then ability to expand and then deflate as and when we need it. So that's one advantage of using dynamically approach. There is no admin intervention here, and there's no explicit calls because everything's done naturally. You don't need a use case to do some explicit calls to add extra memory. It's all done naturally. And then, system is added only when it's needed, and then we give back the memory when it's not needed. So some disadvantages, as I said, since this is a guest-driven approach, the primary VM has to make sure that the VM doesn't go rogue or it doesn't keep expanding how much of it wants. So we need to put a threshold. And there's no way to also, for the primary VM or the host to detect if there's a rogue application running in this VM, and that's allocating, let's say it's doing malloc of hundreds of MBs, and then it's locking it up, and it's never releasing it back. So I feel there's no design yet today that where there's no way for the primary VM to detect some rogue application running in the VM, and to make sure that memory is, it's never given back to the primary VM. So there are other ways of resizing the VM. If you guys are aware of the Linux memory management in the virtualization space, there's something called demand paging. The whole concept of demand paging is we add page by page only when the memory has been accessed. So there's something called lazy access or lazy addition of memory, where you have a process doing malloc. The kernel is not going to give you that malloc memory. It's not going to give you 1 MB of memory. So the kernel is going to actually do the allocation, make sure the page tables are all there. It does the actual memory allocation when the process touches that memory for the first time. So the same case here where we add the page only when the access happens. So I call this more of a reactive way, where when the process does the access, that's when the VM adds the extra page, and then it keeps expanding it page by page. And yeah, this works on pages rather than memory blocks. It's more generic. There are many implementations that uses demand paging. And then it is added page by page, and I think it uses something called ballooning, where ballooning is where you deflate the memory, again, page by page. So there's a concept called ballooning in the Linux kernel. And compare that with the Qualcomm's approach, where this is a more proactive rather than the reactive, where you have a process that's doing malloc, and even before the process accesses that memory, we actually, the pressure builds up, the PSI even generates a memory, the VMRD detects that and then adds the memory into the system, even before the process can access it. So this is a more proactive approach, and this is more, it works on memory chunks, 4 MB wise, rather than 4 kilobytes. And then it's released block by block. And then this also takes care of, okay, so there's one issue with the demand paging is where, as I said, the memory is added only when the memory is accessed. So in case of DMA, the kernel will never know that there's access coming, and then we have having a page fault, and the kernel needs to add a memory. So we need to do some special modification to the DMA alloc coherent, which actually allocates memory for your DMA devices. So we need to do some special changes here to make sure demand paging works. So all of those issues are not present here because there's no DMA access issue, because there's no access issue at all, because memory is added proactively even before a process tries to access that page. So yeah, it works on block by block instead of page. So imagine you're adding the memory page by page, and there's round-trip latency incurred from primary to the secondary, and you're doing it page by page. So imagine the latency. For example, if you want to inflate it by 100 MB, and you're adding it page by page, so that's going to incur a lot of latency. Whereas in this case, it's added block by block, and that block size can also be changed from 4 megabytes to 60 megabytes, where I can add add the memory block by block, so that I reduce the whole latency in the PSI mechanism. All right, I guess that's it.
Thanks. How does this interact with VFS caching? Do you leave a certain amount of memory in excess for guests? How does that work?
So can you repeat the first part, though?
What's that?
Can you repeat the first part?
Oh, yeah, VFS.
Virtual file system, you mean?
What's that?
Virtual file system?
Oh, yeah. So like, for example, when a file is read into VFS and cached, that sort of thing.
Yeah, I mean, I think if there's a file access happening, I guess there's some memory that will be allocated before, and then as part of that, there'll be some stall happening, and there will be pressure building up, and that'll be monitored by the PSI, and then PSI can generate the event and then it can give it to the user space. So it takes care of everything. I mean, you don't have to do any special. That's one thing that's good about this whole PSI things that today PSI is used for widely for scheduler and for low memory killer on Android. So it's a very well robust engine, I would say. So it detects all of your pressure going up, and even if you have a slightest memory pressure happening, it can even in the file system area, that can detect that, and then it can generate an event to the user space.
Okay, thanks.
Anyone from Android space here? All right, thank you guys. Thanks for your time.